2.5 continuity. So if you have a function like this, we have, this is continuous. See, there's no gaps, no holes, you don't lift your hand up at all. And if you have something like this one not continuous, there's a hole in there. People, we call it discontinuous. Okay, you can have a function that goes like this. You have a vertical asymptote, and then something goes this way, something goes this way. This is also discontinuous. Specifically, the middle one, we call it removable. Removable discontinuity. This is called infinite discontinuity. And you can have a different kind of discontinuity. Something like this, let's say. This is discontinuous. We call it jump discontinuity. The main question that we need to answer in today's lesson is how to prove a given function is continuous. How to prove a given function is continuous. This is important, so let's see how to handle this. So we say in order to prove f, a function f, is continuous at x equals a, we prove that the limit of f of x as x approaches a from the right side is the same as the limit of f of x as x approaches a from the left side is the same as f of a. If these three things are the same, then the function is continuous. Is the function f of x equals 2x minus 5 if x less than or equal to 1, or x squared minus 4 if x bigger than 1, continuous? Explain. So again, they're asking you, is this continuous? We don't know like what's the limit? What is a here? Well, usually the key point here is to look at the conditions at 1. Do you see that? So we need to see if, because this is a straight line, it's continuous everywhere. This is a parabola, the U shape, continuous everywhere. But what happens at x equals 1? That's what we need to check. So what do? We find the limit of f of x as x approaches 1 from the right side. We find the limit of f of x as x approaches 1 from the left side. And then we find f of 1. See what we get. So we're going to see which function to use. In the first one, 1 plus means above 1, means the second one. 1 minus the first one. And f of 1, you substitute in the first one, because the condition said when x is less than or equal to 1, use the first one. So 2 times 1 minus 5. 2 minus 5, negative 3. This one is 1 square 1 minus 4 negative 3. This one is 2 times 1 2 minus 5 negative 3. See, all of them are the same. So we say since the limit of f of x as x approaches 1 from the right side equals the limit of f of x as x approaches 1 from the left side equals f of 1, then f is continuous at x equals 1 and hence continuous. Notice something here. When I completed the limit, I did not go through the limit laws again. We are in a new section now. You just pass the limit like in your head and you know it's going to be 1 minus 4. You don't have to do limit the first minus limit the second, and then you do inside square it and then evaluate each one of them. So that's all you have to do in this part, or in this case. You don't have to go in depth. Any questions about this?
So, Professor, we cannot use the second equation to put on f of 1.
No.
Because when I put at the first one, I see negative 3 2 with the same answer.
You can't use it. It's not like a game here. You have to follow the conditions.
Okay, thank you.
So you must substitute it in the first one. If you do it on the second one, even if you get the same answer, it's wrong. Next example, find the number or numbers at which f is discontinuous. Two to the x if x less than or equal to 1. 3 minus x if, and the square root of x if x bigger than 4. So we need to find the number of numbers at which f is discontinuous. So what do we do here is, they said find the number of numbers. We usually look at the conditions, as I said. I see two numbers here. I see 1 and 4. 1 and 4. So we need to check out what happens at 1 and at 4. So we need to find the limit of f of x as x approaches 1 from the right side, and then the limit of f of x as x approaches 1 from the left side, and then find f of 1 and see if they're going to be the same or not. So that's one of them. The other one, the same thing we do with 4, limit of f of x as x approaches 4 from the right side, the limit of f of x as x approaches 4 from the left side, and f of 4. And let's see what you get. So plus, that's when x bigger than 1, and this would be the middle function, and that gives us 3 minus 1 2. A little bit less than 1 is the first function, which is 2 to the 1 2, and f of 1 you replace in the first function also 2. So it is continuous at 2. At 4 plus means a little bit above 4, so you use the last function. That's like square root of 4 2. 4 minus below 4, which is the middle one, 3 minus x, 3 minus 4, negative 1. And f of 4 is the last one as well, negative 1. Notice these are not the same. So the function is, so f is discontinuous at x equals 4 only. X equals 4. If no one has any questions, we have some facts. If f of x and g of x are continuous, at x equals t and k is a constant, then all of the following are continuous at x equals t. First one, f plus g. Number two, f minus g. This means, this is saying the sum of two continuous functions is continuous. The difference of two functions is continuous. The product of two continuous functions is continuous. The quotient of two continuous functions is continuous, provided the denominator is not 0. And a constant times a continuous function is continuous. Also, good to know, all polynomial functions are continuous. Rational functions are continuous over their domain. Same works for exponential functions, logs, and trig. Functions. If we look at a function here, exponential function, or this x squared plus e to the x over x squared minus 4. Let's look at this function. So how can I analyze this? X squared is continuous. E to the x continuous. This means the sum is continuous. Also, x squared minus 4 is a polynomial function, so is continuous. But keep in mind that denominator cannot be 0. This means x minus 2 times x plus 2 is not 0. So x cannot be 2 and x cannot be -2. So x squared plus e to the x over x squared minus 4 is continuous except at -2 and 2. Except at -2 and 2. So now we have a theorem. It says if f is continuous at x equals b and the limit of g of x as x goes to a is b, then the limit of f of g of x as x approaches a equals f of b. That is the limit of f of g of x as x approaches a equals f of the limit of g of x as x approaches a. Evaluate the limit of arc sine 1 minus root x over 1 minus x as x approaches 1. So it's saying you can pass the limit inside a composite function. So in here, if I want to apply the theorem, I can pass the limit inside this as x approaches 1. And as you know from the previous section, if you pass the limit to this fraction, you get 0 over 0. So what we need to do here, we can rationalize the numerator. So in other words, we can multiply top and bottom by 1 plus the square root of x. So what do we get? Arc sine the limit as x goes to 1. On the top you have 1 square minus the square root of x square, and keep this the same like that. These cancel out. Let me finish this. So arc sine the limit as x approaches 1 of 1 over 1 plus root x. So then if you pass the limit here, you're gonna get arc sine 1 over 1 plus 1, 2. What's the angle? It's sine 1/2. It's pi over 6. Yes, go ahead.
So, Professor, in this question, why we don't like find the 0 over 0, like in determinate?
What is it? Y is what?
Why you don't like find the indeterminate like 0 over 0, like you said recently? So you mean like limit x to the 1 and 1 minus spell x over 1 minus x. So when we use when we use limit of law, we see 0 over 0.
Yeah, if you pass the limit to this one, you will get 0 over 0.
But why don't you find it first before you like?
I mean, I told you in the previous section, yes, you go through step by step. You find the limit on the top, limit on the bottom, and then use limit laws, limit of 1 minus limit of root x over limit 1 minus limit of x. And then you do 1 minus, you got 1 minus 1 over 1 minus 1, 0 over 0, indeterminate. But this was the previous section where we had to show, or section 2.4, 2.3, where we had to show that we know the limit laws. We know how to apply them. Here, we don't have, if you want to keep using this throughout calculus, it will take you forever to solve a problem. As I told you, when I did that section, covered that section 2.3, I stated that we need to show all these steps in 2.3 to show the instructor or the reader in general that you know what you are doing. That's the idea. But then in subsequent sections, you don't have to do it here. But you still need to rationalize and show the steps, as you can see.
Okay, I got it. Thank you.
Any other questions?
Professor, can you please just scroll up to the previous problem just for 1 second?
Yeah. Previous, do you mean theorem here?
Yeah, the theorem.
Yeah.
Okay, thank you.